given our maximum tensile stresses and compressive stresses. So in tension, we can only have 125 megapascals. And in compression, we can have 150. The equation we need to use is the same. It's still the bending stress equation. But our calculation for I is going to be different. It'll be a little bit quicker for this one since there's only two pieces. So I decided to break it up with a one horizontal slice and one vertical rectangle here. So you should find that y bar, the location of that neutral axis, 97.5 millimeters above the bottom of the beam. The total moment of inertia of the T-beam is 1.91 times 10 to the negative 4 meters to the fourth power. And we have our y bar, which we're also going to need for the next step. So the premise of this one is we want to know what's the maximum bending moment that we can apply so that the maximum tension in the beam does not exceed 125 megapascals. The maximum compression does not exceed 150 megapascals. So how can we take this information and find what's the highest bending moment we can apply? We're going to assume it's in the direction as indicated. Right, so from the picture, if M is in the direction as indicated, A should be in compression. And you're right, though, we want to check A because that's where the highest compression anywhere in the beam is going to be. So if we're not exceeding the compression there, we're not exceeding the compression anywhere. So we can set A equal to the maximum compressive value. We want to make sure we pay attention to the sign here. So negative 150 pascals, since A will be in compression. So that will be M, which we're looking for, times the distance between point A and the neutral axis. So point A is above the neutral axis, so it's going to be positive. And we can find it's going to be 330 minus 97.5. So in millimeters, it would be 233, or 0.233, converting it into meters. Again, that's positive. It's above the neutral axis. Value of I, we just calculated with our tables. So here, this is going to be what value of M is going to cause point A to be at the maximum compressive stress. And the signs will work out. We have a negative and negative. So we'll get a positive value for M. So the value of M that causes A to be in a compression of 150 megapascals is 123 kilonewton meters. And what else do we have to check then to see is this our answer for M or not?
Check at B2.
Right, because we're not only looking at the compressive stress now exceeding 150, we don't want the tensile stress to exceed 125. So B, because it's at the bottom, we're going to say is the place where we have the most tensile stress. So we also don't want that exceeded. So if we set B equal to the allowable maximum 125, will be negative. And now we have to use the distance between point B and the neutral axis. Point B is below the neutral axis with a distance of negative 97.5 millimeters. And then the I value is the same. We have a negative and a negative, so again, the right side is now positive, the left side is now positive, so we get a positive M value here, solving this equation, that a moment of 245 kilonewton meters will cause point B to have 125 megapascals of stress, of normal stress. Again, you want to be careful here because for non-symmetric around, in this case, the x-axis, these y values are going to potentially be different. So you can't just assume one is the negative of the other, which would happen in a symmetric beam around the x-axis. All right, so we have these two m values. So which is the maximum m we can apply so that we're not exceeding the allowable stress limits in our material? Right, it's going to be A, because if we apply the 245, A is now above the allowable 150 megapascals. So it's the lower of the two would be the maximum safe moment that we can apply to this.